Suppose that MD is a metric space. Our metric M allows us to define open sets in M, which are the central concept in topology, the mathematical study of shape at its most abstract level. So what is an open set? A subset U of M is called open in M when U is a neighborhood of every one of its points. That is, for each point x in U, there is some positive radius epsilon such that b epsilon of x is contained in U. Note that this letter x used in the for all statement is just a placeholder, and we can use any letter there we like. It could be y or a smiley face. It makes no difference in the definition. For now, fix the metric space M as our context, so that we can avoid saying open in M over and over again. But don't forget that this word open always has a context of what space we're working in, and its meaning will be different in different spaces, as we'll see in this video. We've used the word open in two situations previously: open balls in a metric space and open intervals in the real line. It's worth a quick check that these indeed satisfy our definition of being open. To show that an open ball Br of x is open, let y in Br of x be given. We're using y here because we already used x for the center of our original open ball. Then the distance from x to y must be strictly less than r. Its difference from r gives us the positive radius epsilon we seek, keeping b epsilon of y contained in Br of x. This geometric argument directly translates into a formal proof using our definition of open ball and the properties of our metric. A similar argument works to show that open intervals in the real line are open sets as well. Thus, our two earlier uses of the term open check out. One more example is worth looking at. In any discrete space, that is, taking any set we like and using the discrete metric on it, recall that every point is exactly one unit away from every other point. So if x is a point in a discrete space, the ball of radius 1/2 about x, which consists of all points strictly less than 1/2 unit away from x, has just one element, x. Let it sink in for a moment that this open ball contains just one point. Now, what does this tell us about open subsets of a discrete space? We can check that every subset U of a discrete space is open via the definition. Let x be an element of U, and simply take epsilon equals 1/2. Then epsilon's positive, and b 1/2 of x is just the singleton x, which is a subset of U since x is in U. This reflects what we've been saying about discrete spaces all along. The metric doesn't add any structure to the points of the space, and thus the notion of open set doesn't add anything either. Since we've mentioned the real line, and this is real analysis, it's worth noting that we can give a complete description of what open sets in the real line look like. Every open set in the real line is a countable disjoint union of open intervals. Carothers proves this as theorem 4.6. What can we say about open sets in general, though? There are three crucial properties of open sets, other than the definition. First of all, the empty set is open. Our for all statement is vacuously true for the empty set because it has no points. Also, the entire metric space M is open because for any x in M, we can take any positive radius epsilon we like, say epsilon equals 1. Remember that we defined open balls in M in the first place as subsets of M. Second, given any collection script U of open sets, the union of that collection is open. Note that this collection could be finite, countably infinite, or even uncountable. It makes no difference. We're talking about unions of literally any collection of open sets. Let's illustrate this with this collection of two open sets and their union. The argument doesn't change. Given any point x in the union, by definition of union, x is in some open set U from that collection. Because U is open, there exists an open ball around x contained in U, which is then also contained in the union. The third one's a bit touchy, so let's work up to it. Suppose that we have two open sets U1 and U2, and the fact that it's just two sets is now important, as we'll see. If we take their intersection, any point x in the intersection must be an element of both U1 and U2. Now, x is in the open set U1, so there exists some positive radius epsilon 1 with b epsilon 1 of x contained in U1. And x is also in the open set U2, so there exists some positive radius epsilon 2 with b epsilon 2 of x contained in U2. Given these, it's not too difficult to find a radius that works for their intersection. Just take epsilon to be the smaller of epsilon 1 and epsilon 2. This shows us that the intersection of two open sets is an open set. We can work inductively to show that the intersection of any finite collection of open sets is open, which is our third property of open sets. Note that we can now afford to list off our sets, because this is only talking about finite collections. If you think about the argument we just made, you'll see why it doesn't work for infinite collections of open sets in general. If we had an infinite collection of positive radii to stay inside at a single point, there need be no smallest one, and more importantly, their infimum could be 0. For example, if we take each open ball -1 over n to 1 over n in the real line, and collect them together, the intersection is just the singleton set consisting of 0 alone, which does not satisfy the definition of being open in the real line. A quick remark. These three properties of open sets are the axioms for what's called a topology on a set. In this course, we'll focus exclusively on the topology of metric spaces, that is, metric topology. But if you're interested, keep an eye on what we can define and prove using only the word open without mentioning the metric explicitly. We won't go any deeper into this, but I'll occasionally remark on definitions or results being topological, that is, only depending on open sets, or metric. And every now and then, I'll mark things with a little asterisk if they seem like they might be true even without a metric, but aren't necessarily. Given a set A in a metric space, it certainly need not be open. But no matter what it is, we can shrink it into an open set by taking what's called its interior. The interior of A, denoted by A with a little superscript circle, or int A, is the largest open set contained in A. For the set A sketched at the right, we see a mouse-ish shape with solid dots and curves included, and open dots and dotted lines not included, and below it a little sequence of points getting closer and closer to the open dot. The interior of this set A loses all of the points that aren't fully surrounded by points in A, in order to make this into an open set. We lose the tail, the bottom edge, and all of the scattered points in our sequence below. The cleanest definition of the interior of A is to simply take the union of all open sets contained in A. This is automatically open because it's a union of open sets, automatically contained in A because it's a union of subsets of A, and automatically the largest such subset because every open set U contained in A is included in that union, and thus is contained in the interior of A. If we think through those properties, we see that the net effect is that taking the interior shrinks any given set into the largest open set possible, and it's a quick exercise in terms of the definition that a set A is open if and only if its interior is all of A. The points in the interior of A are called, unimaginably, the interior points of A. X being in the interior of A, which is an open set, means that there exists some positive epsilon such that B epsilon of X is contained in the interior of A, which is then contained in A. Conversely, if X is a point such that there exists some open ball about X that's contained in A, then this open ball is one of the open sets we took the union of to form the interior of A. So since X is in that open ball, X is in the interior of A. This gives us an explicit condition for what the points in the interior of a set A are. Let's look at a few examples of interior in action to get a sense for what it does in a metric space. First, with our example set. We lost the points that were not surrounded by an open ball within our set, and we kept the ones that were. Now in the real line. The interior of the half-open interval 0, 1 is simply the corresponding open interval 0, 1. We lose the endpoint of 1 because it has no open ball around it contained in the interval. In fact, the interior of any interval of positive length is simply the same interval with open ends. The interior of a singleton set is empty for similar reasons. For a more interesting set, let's consider the set of rational numbers in the real line. Its interior is empty because we've already seen that every non-empty open interval, and therefore any non-empty open set in the real line, contains irrational numbers. Similarly, the interior of the set of irrationals is also empty, because every non-empty open set in the real line contains rationals too. But so that we don't get too cozy with the real line, suppose we take any set and use the discrete metric, continuing with the extreme, or perhaps extremely boring, behavior of discrete spaces. Every set in a discrete space is already open, and thus the interior of any set in a discrete space is itself. We'll see later that open sets give us the language to express many important concepts in real analysis. In our next video, we'll see that they show us the logically cleanest, and I dare say most beautiful, way to express the meaning of continuity of a function. Before we go any further though, now that we've defined what it means for a set to be open, we should also define what it means for a set to be closed. Our definition for closed sets builds directly off our definition for open sets. A subset F is closed in M means that its complement M minus F is open in M. It should be even more clear that this definition depends on the set M to form that complement. But as with open, we'll omit the in M whenever the metric space is clear from context. Due to this simple definition of a set being closed, everything we know about open sets almost immediately tells us something about closed sets, due to De Morgan's laws. The key facts to keep in mind when thinking about this relationship between closed and open sets are: the operation of taking the complement of a set is its own inverse. If you take the complement of a set, then take the complement of that, you get back the set you started with. Thus, the complement of a closed set is open, and the complement of an open set is closed. The complement of a union is the intersection of the complements, regardless of the number of sets involved. Finally, the complement of an intersection is the union of the complements, again regardless of the number of sets involved. In short, complements swap open sets and closed sets, and they swap intersections and unions. Let's use all of this to see what each of our open set properties says about closed sets. Since the empty set and the whole space M are open, their complements are closed, which are the same two sets again. So the empty set and the whole space are both open and closed in M. Because arbitrary unions of open sets are open, arbitrary intersections of closed sets are closed, which we'll illustrate with just two sets. Given a collection of closed sets, consider the collection of their complements, which are open sets. The union of these open sets is open, so its complement is closed, which is the intersection of our original closed sets. Similarly, because finite intersections of open sets are open, finite unions of closed sets are closed. Given a finite collection of closed sets, consider the collection of their complements, which are open sets. The intersection of this finite collection of open sets is open, so its complement is closed, which is the union of our finite collection of closed sets. Again, these should be easy to remember. Just take the properties for open sets, swap open for closed, and swap intersections and unions. Now let's see some examples of closed sets. Remember that all we need to check is that their complements are open. Again, we should first check that closed balls and closed intervals in the real line are indeed closed. A closed ball BR of x contains all points y whose distance to x is less than or equal to r. So its complement consists of points whose distance to x is strictly greater than r. Given any such point y, d of xy is strictly greater than r, and the difference gives us the epsilon we need. Since the complement of a closed ball is open, the closed ball is closed. Closed intervals in the real line are even easier. Their complements consist of two open intervals, which together form an open set. So closed intervals are indeed closed. We already saw that in a discrete space, every set is open. What about closed sets? Well, any subset of a discrete space is closed, because its complement, which is another subset of the discrete space, is open. So in a discrete space, every set is both open and closed. Finally, in any metric space, a singleton set X is closed. Because given any y in its complement, d of xy is greater than 0 by the axioms for a metric, so we can just take epsilon to be this distance, and this open ball around y doesn't contain x, and thus is contained in the complement. Because this singleton's complement is open, the set X is closed. Using our third property of closed sets, we can see that any finite union of singletons, in other words any finite set, is also closed in a metric space. Perhaps a bit surprisingly, this last result isn't topological. It's possible in some topological spaces for singletons and finite sets not to be closed, but for metric spaces this result is all good. There are two other useful, and logically equivalent, formulations of a set F being closed in M that are worth mentioning. Neither is as logically simple as our definition above, but they give perspectives on closed sets via open balls and sequences in a metric space that are a little more hands-on and give us a better geometric intuition for what closed means. Since open sets were defined in terms of open balls, and closed sets are complements of open sets, we can express what it means for a set F to be closed in terms of open balls as well. F is closed means its complement is open, which means that X being in the complement of F implies there exists some epsilon greater than 0 such that B epsilon of X is contained in the complement of F. Let's carefully write out the contrapositive of this statement. The new conclusion is that X is in F, and the new hypothesis negates this there exists statement. It becomes for all epsilon greater than 0, B epsilon of X is not contained in the complement of F. Or in other words, for all epsilon greater than 0, B epsilon of X intersects F in a non-empty set. This gives us our interpretation of what it means for a set to be closed in terms of open balls. Any point for which every open ball around that point intersects F must be in F. We can include the trivial other direction if we like, but the single implication is the important part. In terms of sequences, a set F is closed means that every sequence in F that converges has its limit in F. So the set is closed under the operation of taking limits. As we've been dealing with sequences a great deal, and will continue to, this can also be a useful way to think about closed sets. Arguing from our open ball condition above is easiest, as these open balls are our targets for convergence sequences. Supposing the open ball condition, let a sequence xn of points in F be given, and suppose it converges to a point x in M. Then the sequence xn eventually stays within any open ball B epsilon of x. So this intersection is non-empty for all epsilon greater than 0, and thus x is in F by our open ball condition. Now suppose the open ball condition fails. In other words, that there is a counterexample to this implication. There exists some point x not in F, satisfying this open ball condition. We can use this to construct a sequence showing that our second condition also fails, by taking each xn as some point in B 1 over n of x intersect F. This sequence will be a sequence in F that converges to X, which is not an element of F. In general, as with open sets, most sets in a metric space are not closed. But just as we can shrink any set into an open set, we can grow any set A into a closed set, which we call its closure. We denote this by putting a bar over the set. In essence, this adds to A all points right next to it, or all points that we can get as limits of sequences in A. For our Malson sequence set A, this amounts to adding the points along the top curve, the tips of the nose and the tail, and the limit of that sequence of points below it. The cleanest definition of the closure of A is as the intersection of all closed sets containing A. This is immediately seen to be the smallest closed set containing A because, as an intersection of closed sets, it's closed. Because each of those closed sets contains A, the intersection contains A. And finally, any closed set containing A is one of the sets we intersected, and thus contains this intersection. We think of this closure as growing any set into a closed set, again by picking up all of the points right next to it. It's a quick exercise in terms of the definition that a set A is closed if and only if its closure is A. We can also think about the closure of A in terms of what its points are. These correspond to our two statements about the points in a closed set, and the proofs are similar. First, the closure of A contains exactly the points x for which every open ball about x intersects A. This essentially guarantees that the closure satisfies the open ball condition for being closed. Said another way, the closure of A consists of exactly the points x that are limits of convergent sequences of points in A, which guarantees that closure satisfies the sequence condition of being closed. With all this in hand, let's look at a few examples of closure in metric spaces. For our example set, recall that the points we add are the top curve, the tips of the nose and tail, and the limit of the sequence of points below. These are precisely the points that we can get to as limits of sequences in our set A, or said another way, points for which every open ball around them intersects A. For the most boring example possible, if we take the discrete metric on any set, every set's already closed, so the closure of any set is just itself. Closure is more interesting in the real line. The closure of the half-open interval 0, 1 is simply the corresponding closed interval 0, 1. We keep all of the original set, but also include the point 0 because every open ball around 0 intersects this set. Or if you like, it's the limit of the sequence 1 over n. Note that because this set changed when we took its closure, the half-open interval 0, 1 is not closed, which you could also check directly. The problem is that it's missing the point 0. In a similar manner, the closure of any interval of positive length is simply the same interval with its ends made closed. Looking at a more complicated set, the closure of the set of rationals is the entire real line, which can be seen in quite a number of ways given what we know. Every open interval contains at least one rational point, so every open ball around every point in the real line intersects the rationals. Or said another way, for any real number x, we can find a sequence of rationals converging to x. Or the interior of the irrationals is empty. However you want to see it, our conclusion is that the closure of the rationals is the entire real line, a situation that's significant enough to warrant the definition of 2 more terms to describe it, which we'll do next. Note that the closure of the irrationals is also the entire real line for the same reasons, but this is only half as interesting. Using this case of rationals inside the reals as our model, we call a set A dense in M when the closure of A is all of M. Intuitively, this means that the set A spreads all through M, or that every open ball in M intersects the set A, so no point in X is any positive distance from the set. Or that every point of X is the limit of some sequence of points in A. The figure at the right is an extremely figurative representation of a dense set in our metric space M, because we can't draw general dense sets very well. Pretend that you see points spread all across M with no open balls missing, no matter how far you zoom in. The closure of a dense set, again, is the entire metric space. Of course, any metric space M is a dense subset of itself, because it already is all of M. That's not so interesting. What is interesting is when we can have a relatively small, maybe even countable, set that's dense in a metric space. When this happens, we call the metric space separable. M is separable simply means that it has some countable dense subset. We've already seen that the real line is separable because the rationals are a countable dense subset. The irrationals are also dense, but not countable. Being separable means that even if the metric space contains uncountably many points, and uncountable sets can be quite unwieldy, we can think about its elements via limits of our nice tame countable dense subset. In fact, one of the ways of constructing the real line uses the Cauchy sequence of rationals to do so. We'll see later on that a number of important metric spaces we've seen are also separable, including C of AB and all of our little LP spaces except L infinity. Before we finish, a few remarks are in order. First, the terms open and closed are opposites only in the sense of complements. Closed sets are complements of open sets, and vice versa, but they are in no way logical opposites. Even in the real line, the empty set is both open and closed, the half-open interval 0, 1 is neither open nor closed, the open interval 0, 1 is open but not closed, and the closed interval 0, 1 is closed but not open. In other words, in general, it's possible for a set to be any combination of open and or closed. Second, whether a set is open or closed very much depends on the metric space in which it lives, which we should recall has 2 parts, a set and a metric. In the real line, that is, the set of real numbers with the usual metric, some sets are open, some are closed, just 2 are both, and most are neither. But in the same set with the discrete metric, every set is both open and closed. Thus, the metric we use determines what sets are open and what sets are closed in a metric space. The more subtle point is that not only the metric matters, but the set too. Going back to our old friend, the half-open interval 0, 1, this set is neither open nor closed in the real line. But as we noted before, any interval in the real line is also its own metric space. In the metric subspace 0, 1, this interval qualifies as both open and closed because it's the whole space. We should be very careful about what the set of points is for our metric space, as this provides the other half of the context for what open and closed mean. The full story here is that if we have a subspace n of M, the open subsets of n are the intersections of open sets in M with the subspace n. And similarly for closed sets, though we won't often have need to use this fact. Well, that was a lot. An overview of open and closed sets, interior enclosure, and finally dense sets and separable metric spaces. There's a great deal to absorb, so please consider it all carefully. In our next video, we'll get back to calculus-sounding concepts by discussing continuity of functions, but now we'll define and discuss continuity for functions between any metric spaces, and we have quite a few metric spaces on hand to use this definition with. Till then,